So this is UV visible spectroscopy in the Jablonski diagram. So we have let's think about these energy level diagrams that we've been drawing since the very first day of the class. So for the particle in a box, we would draw just an energy level diagram. So I'll go ahead and do that as a summary figure here. So particle in a box, 1D PB. Can you understand that? 1D particle in a box. Okay. So we had energy. We had n equals 1, n equals 2, and it was n squared. So n equals 3 was higher, right? And then we had row vibration, where we had V equals 0, J equals 0. I'll put double primes on those. And then J double prime equal to 1. Okay, I'm just going to show a couple of these because V equals 1, J prime equals 0, V equals 1, J prime equals 1. So that's the row vibe energy level diagram. So we've covered both of these. We've done spectroscopy on both of these. Then we had a specific one called a Grotrian diagram. So this one has a name. And let's do one like for helium, where we had 1s2, and this one was 1s2s and 1s2p. So that's enough to kind of show the helium one, where we have electron configurations associated with each energy level for the atom. And then finally today we have the Jablonski diagram. And so in this case, we have like this long box with lines in it, and that's called S0. And then we might have a box with a bunch of lines in it, S1, and then we might have another box with some lines in it. We call that T1. And so this S's and T's in the Jablonski diagram are not term symbols. They're just triplet or singlet. So we're just calling the S's singlet states, or singlet states, we're calling them with a capital S. And for the triplet potential energy surface, we're calling that a T. And then we're labeling from bottom to top, like the ground one is S0, but then all the others are ones, like triplet 1 and singlet 1, triplet 2, singlet 2. So we're just labeling them from low to high with the quantum number. And those little lines that are inside the boxes represent the vibrational energy levels. Remember, we're dealing in a Jablonski diagram with molecules. And so the vibrational levels there's 3n-6 of those, and they're all overlapping. And so this is energy. So I just wanted to draw all 4 of these for you so that you can see that these are all energy level diagrams. Isn't that helpful? So now you have all of the different types of energy level diagrams that we've focused on in the course. And spectroscopy is always differences between the energy levels. So whenever we have spectral lines, it's always an arrow of difference. It's a transition from one energy level to another. And that's the same in electronic spectroscopy. Only now we're going to be dealing with differences in the very complicated potential energy surfaces that molecules have. But before we get into really complicated molecules, let's just focus on diatomics. And so let's start this molecular spectroscopy with the diatomic molecule. And so here's the diatomic molecule, and there's a couple of things that are principles associated with transitions in electronic spectroscopy. And that is this right here, this Born-Oppenheimer approximation or Frank Condon principle. And that is this right here. The electronic transitions occur much faster than the nuclear motions. And so these are vertical transitions in this energy level diagram. So what we have here is we have the potential energy, these little curves, that's the potential energy. As a function of the nuclear coordinates. Oops, let's put that. And for a diatomic, you just have the bond length. So if you map the bond length on the x-axis and you draw the potential energy, you see those surfaces where you have the bonding region is the minimum of that potential energy surface. And so here you have the ground state molecule, and you have, say, one atom fixed over here, and the other atom is oscillating around this equilibrium position. And that's the ground state wave function. If you square that wave function, then you get the position of that other nucleus on average, okay? And that's the V equals 0 ground state. So if we come in here and do an absorption transition, so light comes in, remember the square of the wave function is the probability distribution, or the most likely location of that bond distance, basically the shape of that molecule. So most of the molecules are going to be right here in terms of their internuclear distance, right? That's the most probable internuclear distance. And at that point, it lines up with this particular level up here. That might be, say, V equals 15, V prime. And so the most probable transition would be from V double prime 0 to V prime 15. Because if you look at the upper state wave function, notice it's no longer just a regular sine function. It's got kind of a big lobe here and a big lobe way over here. But in the middle, it's kind of small. If you were to square this wave function, you would have a huge probability of there being a population right here and a fairly large at the other turning point, and then not so large in the middle. This is kind of classical if you think about the positions of the nuclei. Let me get out of the way of my hands. Okay, so they're stretching, right? And they stretch and they kind of stop, and then they turn around and stop. So at the heights of the stretching or compression, they stop and turn around. And so they're more likely to be found in the stretched position than in the non-stretched position or the compressed position. But in between, they're moving very quickly. So this does have somewhat of a classical feel to it, right? If you look at a ball on a pendulum, it's swinging back and forth. It's going to spend most of its time at the ends. If you were to take a snapshot, you're going to most likely get a picture of the pendulum at its limits than down at the bottom. Okay. And so this kind of classical thinking does actually show up here in the quantum mechanics of the excited states, right? Now at the ground state, it spends most of its time in the middle, and that's sort of a quantum effect. But as you get higher and higher in vibrational excitation, it starts to behave more and more classically. Anyway, the point is, this is a vertical transition. And so the most probable transition is, say, in this case, 0 to 15. And so that's going to be the peak in the spectrum with the highest intensity. So what we're getting here is a measure of the intensity. The multiplication of this wave function times that wave function times light would give us that transition dipole moment integral. And so if these wave functions overlap, if there's a large area on this wave function that overlaps with a large area on that wave function, then you're going to get a strong intensity. So that we can draw the transition dipole moment integral like this. So I did 0, I did h nu for light in the middle, and then 15, and I said that's large. Let's look at here. Here's the ground state vibrational level in the upper excited electronic state, V prime equals 0. And the 0 to 0 transition is small. And the reason it's small is because there's really no overlap between those wave functions. There's just a little bit of this edge here that interacts with this edge of that one. And you see the overlap of those wave functions is really small when compared to the overlap of this wave function and that wave function. Can you see that visually? Yeah, so that overlap of the wave functions is the transition dipole moment integral. We're taking those wave functions times each other. And if you have big numbers times big numbers, you're going to have a big result. And if you have a big number times a tiny little number, you're not going to have a very big result. Does that make sense? And so in this vibronic spectroscopy, so vibration and electronic, what you have is that you've got this overlap integral or this transition dipole moment integral called the Frank-Condon factor. So it has a specific name in electronic spectroscopy. It's called the Frank-Condon factor. But it is essentially that transition dipole moment integral that we've been talking about since the first week of school. So Christian asked the question, can I repeat that about the overlap of the two peaks? Okay, so these are wave functions. And I'll go ahead and change my pen color to show the low intensity one. Okay. So for the ground state wave function, I've got, this one is blue, okay? And notice it only overlaps with just this tiny corner down here. And so when I take this wave function times that wave function, I've just got small numbers times each other. And so small numbers times small numbers are going to give a small result. And when you integrate that small result over all space, you're going to have a small intensity. Whereas the red peak, the red overlap, the red shading here on the ground state and the red shading here on the excited state, those are big numbers times big numbers, and they're going to give you a big integral result. And so this transition dipole moment integral, which is proportional to the intensity, is large. So this will give us a large peak. Does that help? Yeah, okay, says thanks. All right, very good. And so this is what's going on in electronic spectroscopy. We have at least two things going on that we can see. We have electronic transitions, so the electrons are changing their quantum states. We have vibrational transitions, and so the vibrations are changing too. The molecule is vibrating differently. And then we also have rotational, which we rarely resolve. So we have rho, vib, and electronic. So they call it rho vibronic spectroscopy. Okay. And if you can't resolve the rotational piece, it's still there, but if you can't resolve it, they just call it vibronic. So if you can resolve the vibrational levels on the electronic spectra, like in the visible spectrum, if you see vibrational bumps, then that's vibronic transitions. If you can't resolve the vibrations or the rotations, it's just electronic spectroscopy, even though all three things are happening. So let's expand this potential energy diagram a little bit more and show that it depends upon the electron configuration. And so this piece here in the middle and this piece here over on the left, that's what we're going to cover in the last part of the course. But what gives us this energy level down here is the various bond orders that we have from the molecular orbital diagram. And so we have bonding and anti-bonding orbitals from those electrons. And as they come together, they make a stronger or a weaker bond. And that stronger or weaker bond is reflected in these potential energy surfaces. And so when the atoms vibrate far apart, then there's less interaction of those orbitals. And so the bonding orbitals are weaker, the anti-bonding orbitals are not as repulsive. And so you end up with less of a potential, less of and less negative energy, so less bonding. And if you separate them out to infinity, then you have no bonding. So as you bring these together, the electron clouds start to interact and there starts to be attraction. And then you come down here through a minimum and then the atoms are too close together and the nuclei start to repel each other. And so then you have repulsion. And somewhere there's a balance between that attraction and repulsion, and that would be the ground state. And so that would be the ground vibrational state. So these are different potential energy surfaces related to the electron clouds. Notice I've shown different populations of electrons. This green box here, the green potential energy surface corresponds to the green box right here. And this green box shows you the ground state for the oxygen molecule, where we have two spin up electrons in two separate pi star orbitals. And that's the lowest energy electron configuration for this molecule. But what if we paired up that electron in one of those pi star orbitals? Well, that would be this light blue one here. So you see these electrons are now paired up and they're still in the pi star molecular orbital. But that's a little bit higher in energy. That would be called singlet oxygen. This is triplet oxygen. So we have two unpaired electrons, add one more, that's a triplet, okay? In this light blue one, we have 0 unpaired electrons, add 1, that's a singlet. So that multiplicity is the number of unpaired electrons plus 1. And so this light blue one corresponds to this energy here. I could put both of those electrons up here in a sigma star orbital. So it to be a singlet. And so that's going to be this energy right here. I could split them apart. I could have one in the pi star, one in the sigma star, and that would be this yellow one down here. And notice we can give these, it kind of is all over the place in terms of the different symbols that we give these things. We give the ground state the X, a symbol of X, and then we can put the multiplicity up here in this diagram. It shows it as a superscript after the X. And then this one is indicating a singlet. It's also giving the sort of a, it's given the Millikan notation. In this case, it's in lowercase. It gives the Greek character for that Millikan notation. So delta G or A1. And then that's going to be a singlet state. Then we have that B1 state, also the Millikan notation. These would be in the D infinity H character table. Those are the Millikan notations of those different different orbitals or overall wave functions. And so then the overall potential energy surfaces, you'll see this when we get to the iodine lab, that we have the X state and the A state and the B state. And our transitions are going to go from the X state to the B state. And so we're going to be going from X to B in iodine. And so definitely want to look at that handout before you do the iodine lab. We've got a couple of weeks before we get to it. So these are the potential energy surfaces. And notice how we've only got 2 atoms and it's already pretty complicated. Can you imagine when we get to something like nitrobenzene or chlorobenzene or any of the larger molecules? It just is very, very difficult to piece out what the potential energy surface looks like. Not only that, but you have, what do you plot it against? You have energy plotted by nuclear coordinates, but which one do you pick for benzene? You have 12 atoms and each of those has 3 coordinates, X, Y, and Z. And so you have 36 different x-axes of which you could plot the y-axis of energy against. And so there's just no real way to plot those potential energy surfaces. So it gets very difficult when you get to things that are larger than diatomics to plot out the potential energy surface. And so let's just sort of back away from that and try, instead of trying to plot those real specific potential energy surfaces, we're going to punt and just, I'll show you some shorthand that we use. Let's think now though, from absorption, we get this molecule in an excited state. Let's think about the fates of those excited states. So what happens to those excited electrons? There's really 4 things that can happen. It can have internal conversion, where it moves from one potential energy surface to another with the same multiplicity. So that means like singlet 1 to singlet 0, or like triplet 2 to triplet 1. But notice it's either T to T or S to S. And then we also have intersystem crossing, movement from one potential energy surface to another with a different multiplicity. And so in this case, it would be like an S to T or T to S. Actually don't even need those little subscripts. You can mark through those because we're just talking about the capital letters at this point. So intersystem crossing is when you go from T to S or S to T, meaning triplet to singlet or singlet to triplet. So what is happening in that case? Well, when your molecule is vibrating around, let's say it's in a triplet state. So you have both electrons are spin up or spin down. The point is that they're the same direction. And they're moving around on a triplet energy surface, and they reach a geometry where there's an energy for the singlet state at that same geometry. So the potential energy surfaces hit each other, they intersect. And there's a probability that one of those electrons can flip, and now it's on the singlet surface. And then it can move around to different places. So the singlet surface and the triplet surface have different minimums, and they also can cross each other. And so if the singlet and triplet surface cross each other, that crossing is at a particular geometry for the molecule. So we excite this electron, we get it up into an excited state, and then the vibrations are occurring in that molecule, and they might vibrate to a place where they're also overlapping with a singlet surface, and then the electron flips, and now it's on the singlet potential energy surface. Notice that no radiation has been released. So these are non-radiative. All we have is a flip of an electron, and now we're on a different potential energy surface. So we're going from one surface to another. And just think about these potential energy surfaces as parking garage levels, okay? You've got different levels of the parking garage. But are those parking garage levels level? No, they're kind of cockeyed sometimes. And you can be on level 2, and you can cross over to level 1 where they're crisscrossing. And so you can walk across that spot and now be on a different level. And you haven't jumped, you haven't made any dramatic changes in energy. So if you can picture that, I can picture it in my head, maybe you can, okay? But you've got these crisscrossing levels where you can drive up, and sometimes you can cross over in the middle where they crisscross. And you have the intersection of these different levels. They're labeled with different labels, but there's a place sometimes where you can walk from one to the other. And so then you can move down the ramp. So the geometry motions in the molecule are sort of ramps in this potential energy surface. And so this level might have a minimum here, and this level might have a minimum here, but they may intersect at a certain spot where the molecule can go from level to level without emitting light. And that's called non-radiative relaxation. Both of these are non-radiative relaxation techniques or paths. Then we have the radiative relaxation. So, well, we have dissociation. I've forgotten about that. So this is where we have a transition from one potential energy surface to another one, and then that one doesn't have a minimum. It just, the molecule falls apart. And so that's also non-radiative. So we can have the molecule fall apart without emitting light. We can have intersystem crossing to a path or a potential energy surface that dissociates. Essentially, dissociation involves an unbound potential energy surface. So instead of a minimum, it doesn't go through a minimum, it just goes out to infinite distance. And then we have the radiative ones coming up, phosphorescence and fluorescence. We'll talk about pre-dissociation in a second. So these are the radiative pathways. So we excite the electron, it may change geometry or not, but then it comes back down to the ground state by spitting out a photon. So that would be fluorescence if there's no spin flip. If there is a spin flip, then it's phosphorescence. So you can have triplet to singlet emission. You can also have singlet to triplet emission. So anytime there's an emission event that is also a spin flip of the electron, so it's going from singlet to triplet or triplet to singlet, then that's phosphorescence. And the reason this has a long lifetime is because that's forbidden. So they can't explain why it happens, but it does happen slowly. It may just be probabilistic, meaning it's technically forbidden, but there's some sort of natural roll of the dice that breaks the rules or breaks the symmetry rules or whatever it is that's forbidding these transitions. But it does happen, but it happens slowly. That's why it lasts, those upper states last for such a long time. And this is what all of your glow-in-the-dark toys are using. So this you charge it up with light, you're building those excited states, and then they stay there for seconds to minutes. And you sort of put that in the dark, and then you can see that energy flowing out of those molecules slowly over time. And so you're seeing the photons that come out from phosphorescence. So the phosphorescent effect is the glow-in-the-dark effect. Fluorescence can be very fast. I mean, 10 to the, minus 10 seconds or so, 10 to the minus 12, sometimes 10 to the minus 15. So singlet to singlet emission, also triplet to triplet. So anytime there's emission from the same spin, so triplet to triplet or singlet to singlet, that's fluorescence. So these are radiative because they're emitting light. So that's what the main thing is. We're looking at the fates of the excited state. So we excite the molecule, what happens to that excited molecule? It can work its way down non-radiatively by transferring to potential energy surfaces and making its way all the way to the bottom, the ground state, or it can reach a point where it has to emit light or prefers to emit light to get back down to the ground state. And so this is what we have, everything shown together. We have absorption, we have non-radiative relaxation, which is released essentially as heat. It is infrared. So if we were to look with an infrared spectrometer, we would see that emission. So even though they say it's non-radiative, they mean visible radiation. So we don't see this transition in the visible, so we call it non-radiative. But the radiation is released in terms of heat. Notice those are vibrational transitions, and so those show up in the infrared. And then we have visible fluorescence, the radiative transition down here. So this is absorption of radiation. This is non-radiative relaxation. And then we have the emission of radiation, Again, these are in the visible range. So I'll draw a circle around these where we're dealing with electronic spectroscopy. And then this is IR up here. Now here's an example of intersystem crossing. So we have absorption, comes way up here because of the Frank-Condon factor. So it's overlapping with this vibrational wave function. It comes down that black potential energy surface. And here, notice these vibrational energy levels are very similar in energy. So it's in this vibrational energy and it has a turning point that's the same spot on the blue potential energy surface. So it transfers from the black surface to the blue surface. And this happens to be a singlet to triplet transition. So there's also a spin flip of one of the electrons when that happens. And so there's a spin flip, and then it now comes down to a lower energy level. It comes down to here, as opposed to this up here, which would be the ground state for this black one. So it comes down to here, and then it emits from this point. So that would be phosphorescence. And remember, I just want to emphasize this every time. Fluorescence is fast and phosphorescence is slow. And you can just think about it as a probability, rolling the dice. It's like getting, you know, like if you play Yahtzee, you got to get 5 of the same kind. That happens much less than getting 3 of the same kind. So fluorescence might be getting 3 of the same number, and phosphorescence might be getting 5 of the same number. And so it's going to take longer for that to happen. This is dissociation versus predissociation. Notice if I have this particular overlap of potential energy surfaces, this part of the wave function down here actually would send the molecule up into this region here. And notice there's no vibrational levels up here. And so we don't see any of these vibronic transitions. We just see a smooth continuum. Because if we excite the molecule to right here, you can think of this classically like a ball rolling down a hill. If I put a ball right here in this particular carnival game, it's not going to get stuck in the bottom. It's going to roll through there and have enough energy to dissociate. Can you see that? Y'all ever played it? I don't know. I haven't seen this in a while, but it's a carnival game where you have a bowling ball on the hill and you're supposed to roll it up over this hill and get it stuck in this little minimum on the other side. But the geometry is such that the momentum of that bowling ball goes over the little hill, up the back, and then comes back over the little hill and comes back to you, and you don't win the prize. And so you've got to find just the right height to give it just the right energy to get over the little hill and then not come back over the little hill. And so you got to find the frictional coefficient on the other side of that hill that is enough to slow it down between the little hill and the back ramp. And this is kind of what I think of when I see this. If we have a molecule that's excited from this part of the wave function, the left half of this wave function, then it's going to have enough energy to dissociate when it's absorbed. And we will see this in iodine. When we're doing the iodine experiment, we'll be labeling these transitions. Like this might be the V double prime equals 0 to V prime equals 12, okay? And then this will be 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, and they get closer and closer together. And then after 22, we don't see any more bumps. And that's because we've hit the dissociation limit in iodine. And so you're going to assign those vibrational peaks in the iodine spectrum. Now, sometimes you're assigning these peaks, V equals 1, V equals 2, so on. And then you have this gap here where you don't see any vibrational transitions, and then they pick up again. Now, we won't see that in iodine, but you do see that in some molecules. And that's just because these vibrational levels here overlap with the dissociative potential energy surface. And that's called predissociation. So you have not given the molecule enough energy to be directly dissociated, associated, but it hits an unbound state, and you have either intersystem crossing or inversion, depending on if there's a spin flip necessary or not, and then you have a dissociative state. So that's pre-dissociation. So that's also a non-radiative relaxation path. And so now let's compare the spectroscopy of these two things. So we have emission and vibrational spectroscopy. So I've color-coded this. Notice you have this green ground vibrational state, and it's going to overlap with the excited states. And so one of these is going to be the best overlap, and so that's going to be the maximum. So this maximum peak corresponds to this vibrational level right there. Okay, and this one here corresponds to this one here. Okay, so hopefully you can then see that all those peaks are up there, and that's the absorption spectrum. Notice how these arrows are longer. So this is wavelength increasing in this direction. So this is long and short. Uh-oh. So this is high energy over here and low energy. So the longer arrows, so this will be the longest arrow transition. So that would be this one up here. So does everybody see that? The absorption spectrum is at the short wavelength side. This is a really important piece. So the absorption spectrum is on the short wavelength side, and the emission spectrum is on the long wavelength side. So why is that? Well, you have radiationless decay. So you have the molecules that are excited drop down to the ground state, ground vibrational state in the upper electronic state. And so then now we have this red vibrational wave function, and then it comes down and hits these levels. So it's overlapping with the vibrational levels in the ground electronic state. And so notice all of these arrows are shorter. So this is a shorter arrow than the absorption arrows. And there might be a little bit of overlap between the 0 and the 0 transitions. And so you might have an up arrow that is this long, and you might have a down arrow that's also that long. And so that is the 0 to 0 transition. So notice my notation here. I have the double prime, which gives us the lower state. So the 0 to 0, when the arrow is going towards the prime, so we're going lower to upper, that's absorption. And then when we're going prime to double prime, that's emission. And they have the same arrow length, so they have the same frequency. So the 0 to 0 transition is the only place where these can overlap. That's the only place where the arrows can be the same length. Now, if you're looking at this on the video, or if you go back to look at this, I want you to stare at this and listen to this slide over and over again until you understand why the 0 to 0 transition is the only place these spectra can overlap. That's the only place where the arrows are the same length in the energy level diagram. In all other absorption, the arrows are longer, and so they're going to be at the short wavelength side. In all other emissions, the arrows are shorter, so they're going to be at the long wavelength side. So I'm going to pause there in case you want me to clarify. Can you see that if we're in this ground vibrational state in the upper electronic state, that all of these arrows are going to be shorter than that one, right? Because they're hitting vibrational levels that are higher in energy. There's that arrow, there's this arrow here. It's going to hit that level, and it's even shorter. So it's going to be a longer wavelength. This one is going to hit the next one. It's even shorter than that. And so it's going to be an even longer wavelength. And so all of these emission peaks are at longer wavelengths than the 0, 0. And then all of these absorptions are going to be at longer arrows than the 0, 0. They're going to hit these levels here. And those arrows are all progressively longer. And the longer the arrow, the larger the energy difference, which means the shorter the wavelength. Okay. Now we say, look, this is getting complicated with all of these overlapping energy level diagrams. So then we're going to show the Jablonski diagram. So that's what this is. This is a shorthand for all of these potential energy surfaces. And so this blue box is representing the ground vibrational state. So you see that S0 over there. S0 is telling you the ground state is a singlet. The 0 means ground state, S means singlet. And so instead of plotting this by internuclear distance, because when we get to bigger molecules, what are we going to plot by? The CH bond length, the CC bond length, the angles? We have too many variables. And so we just forget it altogether. And we just draw a box and we put in there all the vibrational levels, and we don't care about their spacing. We just show there's a bunch of vibrational levels in that box. So do you understand what that box means? It's the bottom of that box is the ground state energy. And then all of those levels above that are just the vibrational levels. Then we have this orange one here. That's the singlet. So see, it's the black potential energy surface here. This is the singlet. That's the ground state, ground vibrational state for the singlet. And so that's the energy that's plotted up here. And then we draw those levels just to indicate the vibrational levels in the singlet state. And then we have the triplet state. Notice its energy down here. The box stops at that vibrational energy level. And so that's going to be shown over here as the triplet state. So we're getting rid of the internuclear distance. We're just drawing these boxes next to each other. And the order really doesn't matter. We could put S0 on the left and S1 on the right and T1 on the right of that, okay? So that's the Jablonski diagram. It's just a simplification of these potential energy surfaces. And we have no geometric information in it at all. It's just an energy level diagram. And so let's talk about all the different things that we've covered in terms of the fates of the excited states. So this is what's happening when we have absorption. So we have blue light absorption, short wavelength absorption. We call that the pumping the molecules to an excited state. If we're going to do spectroscopy on this, a lot of times we want a really bright absorption source. And so we pump those molecules up. Then they can do several things. There's 4 or 5 fates of those excited states. So we can have intersystem crossing, we could have internal conversion and so on. So it can like rattle its way down to the ground state in the singlet state and give off a little bit of infrared heat. And that's non-radiative relaxation. It's just distributing that excited energy in the vibrations of the molecule. And also you might have collisions and that gets rid of some of the energy. Then it can do intersystem crossing where it can go to the triplet state with the spin flip. And so then it can rattle its way down in the triplet state. Still, it's not emitting any visible light. Okay? And so that would be, or it could do internal conversion and go all the way to the ground state. So it could do this path. So you see we have different paths. It could go here. That was path 1. It could go here. That was path 2. We could do another intersystem crossing right here and get to the singlet state and go all the way to the bottom. And so for this particular molecule, there's a way for it to get rid of all of that energy without emitting visible light. It could just heat up like crazy. Or it could emit light either phosphorescence or fluorescence. It could go straight from the S1 down to S0. So that would be the fluorescence pathway. If it came from here straight back down, that would be fluorescence. Or after that intersystem crossing, it could have a spin flip and an emission, and that would be phosphorescence, and that would give us visible light. So here's all of your fates of the excited states put on one diagram, and the difference between radiative and non-radiative. Okay. We don't show dissociation on here, but some of those states could lead to dissociation or pre-dissociation. So do you understand the Jablonski diagram now? It's just a simplified energy level diagram. It shows the electronic energy levels and the vibrational energy levels. And the vibrations we associated with non-radiative relaxation.